vulnerabilities and or software security, and we saw that the major type of software vulnerabilities is the buffer overflow. And last time we started to see the idea behind buffer overflow. We said that you have the execution stack, and then you have variable there, and you might allocate arrays in the stack. So the problem is when you fill up an array on the stack using data supplied from the user, user input. Okay. So the user input here, normally the size of the array here is 500, but since it is controlled by the user, he might supply more. And if he supplies more, the user, other variables will be overridden. Okay? And you can override, we saw last time, you can override other variables. But also, you can store context information stored in the stack, or you can override context information stored on the stack, in particular, the stored EIP, which is the return address. And if you override that, basically when you return from that function, you'll be transferred to wherever you override. Okay. So here is an example of vulnerable program. So this vulnerable program, what it does, it declares an array of size 100 will be stored or allocated on the stack, and then that array will be basically we will copy argv into buffer, and argv, this is the user input. Okay. So we take the user input, we put it into buffer. So if that user input is less than 500, we are fine. If it is more than 500, it will override other stuff. Okay. And so the idea here, or the goal of the attacker, is to override the EIP. Okay. So if it is more than EIP, you will override everything. A lot of information on the stack, and in particular the stored EIP. So we saw last time that you can override the EIP here with an address of a certain function, let's say CMD or shell or whatever, which is already there in the and loaded in the current execution. But the problem is this is not stable. You can't know exactly where that address is. So this is why a more stable type of exploitation would be, since you have a lot of buffer here, 500, you can supply the malicious code here, and then instead of putting an address to jump somewhere else, you will jump back to that code. Okay. So basically, you will send the code and you will make the vulnerable program execute. Okay. So this is the idea. You override basically you have control over all this gray section. Okay. All this you have control because this is user input. So basically, you will craft that user input such that at a particular location, which is the location where you override the IP, you store you put the address of an address that points back to the same buffer, and in the same buffer you put the shell code. So shell code, basically the name, it's a small piece of code that is supposed to give you shell control. So basically shell is command line. Basically we have full control over the victim. But that name is now used for even if the exploit will give you other things, like if it opens a port, for example, or it executes another program. Okay, all this is called the shell code. Okay, and shell code will not go into the details. So the shell code is very concise code. Okay, piece of instruction, assembly instruction, that is independent of the machine, of where it is executed, and it is supposed to do something that the attacker wants.
The shell code that has to be specified as a single processor. So, for example, Intel processors. It will not work on
of course, and it depends on the architecture. Okay, so here shell code for Windows, for example, is different from shell code for Linux, for example. Okay.
Doesn't it depend on the processor? So if it's Intel,
both, of course. I mean, if these are machine instructions, assembly instructions.
Yeah. Okay.
So assembly instructions, they depend on the architecture and they depend on the OS also. Okay. Well, you cannot have an executable for Linux that runs on Windows, right? Although it's the same architecture. Okay. So you need to have the same architecture, Intel, as opposed to ARM or some other, and also the ICS. Sometimes the shellcode is there for a particular version of Windows, because it is based on having, I don't know, some resources somewhere exactly for a particular OS. Now, code mobility. This is an interesting part here. So here in the simple scenario, here you need to guess exactly two things. You need to guess exactly where the EIP should be overwritten. So you need to guess it. This offset here, you need to guess it exactly. Okay. And you need to guess also the location of the shellcode.
But it's easy because you are done.
Yeah. But it depends on this offset also. It's quite relative. Now, this makes the exploitation not very portable. So it might work in some scenario, but some other scenario, it might not work because most probably you might have some other information put here. So the stored EIP might be 4 bytes away, or 4 bytes before. Okay. So to make the exploitation more stable, what you do, since you control all the buffer, what you can do, you can, after you place your shellcode, since all this is just junk, you can put anything, you will place the same address, you will repeat it. And then the wherever the EIP will be located, so it might be here, it might be here, it might be here, it will hit the stored EIP. So basically you can repeat the return address here. And then and here the same thing. You are not required to jump exactly here. So basically what you can do, since all this also is junk, instead of putting anything like A or B's or any byte, you will put this 90. 90 stands for what?
No.
These are NOPs, no operation. No operation as simply what it does, it just does nothing. It moves to the next instruction. Okay, just move the next instruction, move the next instruction. And then here, if you put a lot of NOPs here, wherever you jump here, if you jump for example this 90, it will drive you to the next one, etc. until you reach the shellcode. So this is why this is called NOP slide. So like slide, you fall anywhere, it will drive you back to the shellcode. Okay. So here is to improve the portability of the exploitation. Okay. So you repeat the return address here, and then you put the NOP slide. Okay. There are a lot of other techniques to improve this, but these are the basics. These are the protection against buffer overflow. Okay. Yeah, let's do it because I want to show you how the buffer overflow works in practice. But let's discuss it because we're going to discuss it in the small demonstration. So how to protect against buffer overflow? So basically, there are two techniques to protect against buffer overflow exploitation. There are techniques that the programmer or that are applied when you compile your code. When you write your code and compile it, there are a couple of things you should do in order to avoid buffer overflow. So these are the things. So SQL coding, basically you need to check anytime there is a buffer which is overwritten, or you take some data from the input, from the user input, and you put it in the buffer, you need to check the size. And basically, any operation on an array, you need to check that it is within the boundary. Okay. This is of course in C, but if you take Java, for example, Java, this is done for you. Okay. Now you need to follow secure coding practices. This is for buffer overflow, but if it was for another type of vulnerability like a string format or like a race condition or like a SQL injection or whatever, there are, you need to take into consideration when you write your code. So this is why you need to, a good programmer to produce secure code, he needs to be aware of what might happen if I write this or I write that. Okay, so secure coding. Okay, secure coding. Then StackGuard, Propolis, StackShield. All these. So basically, all the three. These are techniques applied by the compiler. So basically, the programmer has nothing to do with this. Maybe he can enable or disable these features in the compiler. Okay, but these are features that are implemented in the compiler itself. Okay, so all this for code generation. So you can protect against buffer overflow when you generate your machine instruction, basic compilation, writing the code, source code, etc. Okay, this is one part. And then the other type is operating system measures. So the operating system has, or most of operating systems have protection features against buffer overflow. Okay, or in general we call them memory corruption attacks. Okay, so you have DEP and ASLR with this stuff, so basically to see how important these measures are. Now, for example, in DEP, it's enabled in all recent versions of Windows, and in order to disable it, you need to do it from the BIOS. Yeah. So because it's so important. Same thing with ASLR. I think ASLR you cannot even disable it. It is there and it can't be disabled. In recent Windows 10, for example. Okay. Now I will go through these one by one: StackGuard, Propolis, and StackShield. So StackGuard. So placing a canary value between local variables and the return address. So here, the technique consists in the following: you have the stack. Normally, you have stored EIP, and then afterwards you have stored the EBP. The idea here is to place a small random value, so that because if the buffer wants to, if you put more data on the buffer to override other variables, it will override in this direction, right? So in order to override the EIP, it will override everything before. Yes. Okay. So basically, you will put some value here, and you check if that value is overwritten or not. Whenever the function returns, you will check if the canary value put on the stack has been modified. Okay. This is what's called canary. Canary, you know what's canary, right? It's a bird that makes a lot of sounds. So when you compile your code, the compiler will insert that value, which it's a random value, which is difficult to guess. Because if you can guess it, you can override it with the right value. So here it will be difficult to guess, and it will be checked at any time you return from this stored EIP. Okay.
It's like a hash function or a hash.
Random value, let's say random value. Random value difficult to guess.
Like in the methodology, it's like making authentication of.
Yeah, you can see it if you like.
Checking.
So basically, I will between the local variables and the return address. So here, this is an example of how this is done. So if you compile your code with that feature, canary value enabled or StackGuard enabled, you will have here, see here, push L. This will push this value onto the stack. This is the canary value. Okay, and then when the function prologue, this is whenever you enter a function, whenever you call a function, you have certain things to that are always done. Okay, so basically here you push, in addition to push EBP and subtract this from ESP, etc., you will push that value. And function Epilogue, this is what happens when you exit from the function. Okay, when you exit from the function, see here, leave, and then compare. There is a comparison. So you are checking. Of course, you need to store that value somewhere else. That value should be stored somewhere else. And whenever you exit, you will go to that value stored on the stack and you compare it with the value you know that you placed there. Okay. So here you compare, and this instruction is what?
Jump if
Jump if not equal. So basically, if it is not equal, to jump to to some function that will terminate the program because the canary value has changed. Okay. Yeah, jump if not equal to canary change, and here canary death handler and
now, this can be avoided. I mean, if I, for example, in the buffer itself, I insert a jump instruction to the malicious code. So I just do this normal Stack Overflow attack.
Then
If it's changed, I know if the program closed, I know that there's a canary value, for example.
okay.
In that case, I will just write the jump instruction after the buffer, just immediately after the shell code.
But you don't know the size of the canary value.
I don't
You can't read.
I don't understand. What do you want to do? What do you want to do?
Alright, I just insert the knobs like normal to check for.
So you override the buffer,
Yeah.
right?
I will override.
Then here, what you will override the EIP or not?
No, I don't. I will not override the EIP. Just insert a normal jump instruction
Where?
in the buffer itself.
Here.
Yeah.
How will you read?
How it will be executed? How you will make the program execute that instruction?
Has to be after.
It's a data there. You are placing a data, and the whole fact of overriding the EIP is to get the execution control. So you have to execute to override the EIP so that when the function exits, you will resume execution from that EIP which is stored.
What did we do? I mean, a few slides ago, we said we have multiple EIPs, multiple malicious EIPs.
Yes. Yeah.
So
Yeah, the multiple EIPs. No. Here, the stored EIP here. Basically, why we repeat this? Why we repeat this?
We don't know where.
Because we don't know exactly where to override the EIP exactly.
Mm.
That's it. But only one of them will be used here.
Yeah, only one of them. So, but for example, one of them is not. I mean, one of these malicious EIPs is exactly where the EIP is.
Yes. Yes.
The rest are not in.
Yes. Okay. But what we can do with the rest?
You'll use one, and then that's it. I mean, you only use one.
You use one. But to use one in the case of Canary, you cannot use it if you cannot use it without changing the Canary bar. So to reach this, you need to override everything.
Unless you know where the canary value and the value of the canary value.
Yeah, if you can guess the Canary value, it's another story. Yes.
Can we know where the canary value is?
Where?
In the
You can.
Then pass it and override it.
Okay.
How can you budget?
How can you pass?
Know the size of the value.
Yeah, of course. Yes, that's fine. Okay, but then how if you want to override this, you have only one weapon in your hand, which is this buffer.
Alright.
Here you need to decide what to put in the buffer. So if you want to override this, you need to override everything before. Okay.
So, if we, for example, assume that we override the canary value and we jump to our malicious code,
Yes.
then we will execute our malicious code right away.
No, but before you
No.
check before
When the execution will jump there, when the function returns.
Oh, return. So
Yeah, but because the stored EIP, this EIP will only be used only at the end of the function.
I see.
And at the end of the function, basically before returning, here, see here. This is the return. This is the return where you will get control. The attacker will get control. But before that return, what happens? You will check the canary.
So
The canary will be checked before the return. Okay.
Yes.
Okay, let's leave the name of our next.
You said we can know the canary value, right?
It's how to use.
What do you mean by mechanism? You can know the location. You can guess the location. Okay, fine. You know that the canary value, for example, is just before the stone.
But we cannot know the value.
It's 32 and 5.
It's random, and if every execution has different value. Yeah. Okay. Yeah. So this is the idea of canary value, and this is implemented in almost any compiler. So any C compiler have this. You can disable it. You can disable this. Okay. Whether Linux or Windows, but it is by default it is enabled. Okay. Yeah, stack random. So now, for example, in Microsoft, when you open Visual C++, you have this /GS option when you compile. So here, it's the same idea, canary value, but the canary value is placed between local variables and the stack base pointer. Okay? So basically, here, this is the base pointer, and the local variables are all this, and the canary value is between. So basically, same thing. It will prevent you from overwriting the EIP without overwriting the canary value. StackShield. This is another feature to protect against buffer overflow. And here, the idea is to save the return address in another memory space. Okay, the return address. So your goal is to override the EIP, right? The EIP, stored EIP. Okay. Now, if normally when you go inside the function, when you call a function, okay, the return address will be set on the stack. When you exit from that function, that return address should be the same, should not change. So here the idea is to check if that return address has changed or not. So basically what you do, when you call a function, before starting execution of that function, you go and store that value of EIP.
Yeah.
And then, in another return address somewhere else.
So
In
basically,
some
the main,
structure.
if this is a normal code in the main function, the main code,
Yes.
I will set this address.
Where it is stored, I can't tell you exactly where it's stored, but it is stored in some, anywhere in the game, whatever, some array which will hold the correct return addresses. Okay? And so on entry, the return address is copied from the stack to a return array. On exit, the cloned return address can be checked against the one in the stack to detect possible attacks. So again, the goal in the buffer overflow, our goal is to override this during the function execution. And then if the compiler can check whether that value has changed or not, it can detect if that EIP has. So this is the StackShield.
But if you have it like stored somewhere else, you don't need the stack to be. You don't need the EIP in the stack to be.
Maybe you need the order.
But you see, so basically what you need to do, you need to restore it from that.
Somewhere else, not there.
So it's in the stack. So basically it's not an easy process. It's not a matter of okay, I know where is the return address. I will take it from there and put it there. Okay, it's dealing with the stack is about pushing and popping. So this is how we fill the stack. Yeah. Now, Propolis SSP. This is implemented in Linux when the GCC. So the GCC compiler implements this. Implements 3 protection measures, which are a random canary value before the EIP with 24 bytes instead of 4. So instead of just 4 bytes, you will have 24 bytes. Okay. So basically 6 words. Okay. So it's long one. So even if for brute forcing it will be difficult. And also reordering local variables on the stack. Remember the example we saw last time, when you have an array target and a real attacker, and then we overrode the TTs with the Ds, if you remember. Mm-hmm. So here it depends on the order of the variable. So here this is one other feature. If the goal of the attack is to override some value or some variable value with another variable, okay? So reordering, replacing the variables will prevent that. So we will make the attack not very stable. Reordering local values on the stack. By placing all non-buffer values in lower addresses, they are protected from overflow by buffer variables. Yeah. And copying function arguments to local variables. Copying function arguments to local variables. This protects them from overflow. So here the idea is, remember, yeah. So suppose you have a buffer here. If you have a buffer here, it will override the EIP, the stored EIP, the EIP, but also it can override these 592. What are these 592? These are parameters. Okay, Okay. Now to protect these parameters, what you can do, you take those parameters and you copy them somewhere here. Yani after the buffer variables. So basically, even if you have buffer overflow, can it override the upper ones? It can't. Because the memory, again, it moves downward. Okay? So basically, you can override, but you can override all this. Everything up, it will not be overridden. Another technique, so to protect the parameter values.
Now you said that this is implemented by the GCC compiler.
Yes.
But when you did the code GCC, the ordering wasn't happening.
Yeah, the reordering, yes.
Is it a feature or I have to specify it?
Yeah, you know, with GCC you have a lot of options. Lot of options. For example, you can, I think the canary you can disable it by typing. We're gonna do it. -fno stack protector. Yeah. So stack protector is the canary stuff. So if you do this, it will be disabled. The canary. So you can enable and disable them using the options. Yeah. So this is the idea of. Okay, let's stop here.